Okay, so we are here. We are discussing the wavelet transforms and the other transforms. So whenever we have these transforms, the focus. First of all, there are several types of transformations which we kind of started discussing the last time, and we were discussing also the possibility of representing any type of transformation in linear algebra or using the principles of matrices. For example, one of the types of transformations could be the Fourier transform, and this Fourier transform in the analytical expression, which means that which can be represented in a classical integral of some data sets from fx, and here we have ikx dx with the integral from minus infinity to plus infinity. This would be the Fourier transform, and the inverse of this one would be the integral from minus infinity to plus infinity of fk minus jk x dk. So here we are integrating over x. We have the limits of the integral, so the result it should be a function in k. In a similar way, here we are fk, k, k. We are integrating over k, so the result overall it will be a pure function of x. Now this type of Fourier transform, and this would be the inverse Fourier. These expressions they correspond to continuous functions most of the case, and this one it should have also an equivalent which can be represented by transformation matrices. And these transformation matrices, they are, instead of having this integral, we are going to have a summation over few terms, where we're going to sum over some n, which can go from 1 to n. And then all of the functions that we are going to deal with, there will be, here we have f of x times r x u. Okay, so actually this u, this is, let's try this one, xk. So we have a, so this is one-dimensional data set, and what we mean with one-dimensional data set is that just function f of x, it depends on x. So this means that instead of being a continuous function, it could also be represented by discrete data points which are found at some delta x in this way. And now these f of x's, here they are. In case the f of x, it is 1, 2, 3, 4, 5. It is 5 data points. F of x is equal to f1, f2, f3, f4, and f5. This is a vector which is 5 by 1. In case we have a summation, and in fact, let's think for a moment. This is going to be equal to f k, or let's call this one fm equal to k in k. So each value of the function f in the new domain, it is going to be represented in this form. So now, once we have this kind of representation, we can also expect the following. So we have here this vector fk. This is going to be a vector which is 5 by 1, and this can be represented by a matrix which is 5 by 5, multiplying another vector which is 5 by 1. So 5 by 1, in this case, they are the values of 5 values of f of x, which are shown here. And then we're trying to come up with a matrix representation, which for the Fourier transform, we kind of derived also in the previous session. Now, this type of transformations, we use a notation here denoted by A, and this A, it was a matrix, and the one-dimensional transformation, this can be represented here as PU, but this PU, it is one, it's a vector. This would be the summation from 0 to to n minus 1 of the values of f of x times r x u, and this is equivalent to reporting that a vector t, this is equal to a matrix A times a function f. Okay, so this is the matrix A we are trying to come up with. Now, at the same time, we can represent also the inverse of this function, where we have f of x would be equal to summation u0 to n minus 1 times, here we have tu, all the values which are now in this vector, times s x u. So now this is the inverse transformation function, the s x u. And now this type of representation here, this is equivalent to having that f is equal to the transpose of the transformation matrix A times a vector t. Now, this is the one-dimensional case, which means that one-dimensional case, it will be a representation of the values of f as a function of x. We have also the two-dimensional representation, and in this case, f would not be just a function of x. So let's write this. This is one-dimensional case. For the two-dimensional case, we'll have the f being depends on x and y. And this representation would be a very good, how can I say, equivalent principle with the images, where an image, for example, it is going to carry some specific pixel values anywhere over an array of numbers, 300 by 300, which would be a traditional, not traditional, but some image which we can view on a monitor. If it is anything 20 to 20 pixels, it might be too small for us to distinguish some features. But in this case, this is the one-dimensional case, and the two-dimensional case, we can represent this one as t as a function of u and v. This would be equal to the summation of y0, and this is x0 to n minus 1, of the f of xy times r, and now this function r, it is going to depend both on x, y, u, v, and this one, it will be, this is also equivalent that this new transformation of the data, this can be represented as a matrix A, transformation matrix A, times the two-dimensional data times A transpose. So if you notice something different is that the transformation matrices now this is a matrix, vector, but now since the data set is two-dimensional, this is a two-dimensional array, and we are trying to transform this one. But once we are trying to transform this one, we are multiplying from both sides by a transformation matrix A with its own transpose. Now, similarly, we can also construct the inverse of what we just wrote down. So we can say that f of x and y, this will be the summation over u and the summation over v. Now, these two summations will change from u from 0 to n minus 1, and this is also n minus 1. And the function that we will transform, it will be this one. Sorry. Lección. I'm in a class, okay? Lección. Sorry for this. So this transformation, this will be, we have to modify this one with x, y, u, and v. Okay? And this representation then, this will be this function here. This will be equal to A transpose times P times A. Okay? And one other essential element that we could mention here, and probably we should mention, is that the inverse, so for example, we can also notice this one even from here. So in principle, this was T was equal to A times F, and we can write this one A times, so F is equal to A transpose times T, okay? And if this is true, actually we're trying to deduce something we're trying to deduce something which probably we already know, and probably we mentioned this the last time. We see that this A times A transpose, this should be equal to an identity matrix, which can be I n by 1 times T, because we have the T is equal to T. And what is this identity matrix? An identity matrix is a matrix which is full of ones in the diagonal, right? And so it's not going to edit any information on the vector. So what we also observe, or what we can also add here, we can also add the fact that a transformation matrix, it is going to correspond to the inverse. So let's say if we have a function transformation, let's call this one wavelet transformation, WT, or Fourier transformation. So this one, it can have representative matrix A. Now the inverse of this wavelet transform, let's consider the inverse, this is equal to A transpose in case A, it is a unitary transformation. Unitary transformation, so A, it is a unitary transformation. Now, unitary transformation is a transformation where all the columns are orthogonal with respect to each other, and also they are orthonormal, which means that, so initially what was there, they were orthogonal, and being orthogonal, that simply means that we can have two vectors, which if we calculate the dot product, we're going to get a 0. And the orthonormal, it means just a vector which has length equal to 1. Okay, so this is the properties that the transformation matrix A should have. And all of these transformations, in fact, if we can calculate the Fourier transform, which is probably one of the most scariest functions, at least for me, when I was a student trying to calculate integrals that look like this, j, k, x, dx. Once I look at this expression, this is an integral, it has a kernel, and the kernel in this case, this is the kernel, which conducts the transformation. Now, kernel, in the language of signal systems or image analysis, this also, it is equivalent to a filter, okay? So it is slightly different here, but since we're discussing Fourier transform, it's also the time probably to mention this one. And so if we can represent Fourier transform using linear algebra, then things can be very, very easy. But as we said here, A inverse, it is equal to A transpose in case A, it is orthogonal and also orthonormal. Now, let's try to provide an example regarding this. So a matrix which can do this would be a matrix A, which can be equal to 1, 1, 1 minus 1. So first of all, let's check if two columns of this matrix are orthogonal. So to check the orthogonality, we have to take the inner product of C1 with C2. So inner product of C1 with C2 is equal to C1 transpose multiplied with C2. C1 transpose of this element, this is 1, 1, transpose times 1 minus 1, and this will be equal to transpose of 1, 1, it's this, multiplied by 1 minus 1, and this, it is 1 by 2, so 1 row, 2 columns, and this is 2 columns, 1 row. So the result is going to be simply a number, a scalar, and here we have 1 times 1, 1 minus 1, 0, 1 minus 1, this is equal to 0, so this is orthogonal. So that's good. We have a matrix A, whose columns they are orthogonal. So this is a good candidate for being a transformation matrix such that which can be unitary transformation matrix, and at the same time, its transpose could be equal to the inverse function at the same time. So that means that it can be easy for us to calculate the inverse, the transformation, and the inverse. Now, how do we check for the orthonormality? So the orthonormality, we just have to check what is C1 times C1, which means multiplying the same column with itself, and we have to check whether this is equal to 1. So this is the question. Let's do this. So if we take the transpose of column 1, this is going to be equal to 1, 1 times 1, 1, and this is equal to 2. So it looks like this is not orthonormal. Not orthonormal. And in order to do this, to make this orthonormal, then we could multiply the whole matrix by 1 over square root of 2. Okay? In fact, we could just multiply this column, but we can make sure that the second column needs to be normalized by this one also. So in order to normalize, in order to normalize 1, 1, we just transform this one, or we rewrite this one, 1 over square root of 2, 1, 1. Okay, then we can also check the other column, which is 1 minus 1, and we can notice that that one can also be made, can be, so this is 1 minus 1 multiplied by 1 minus 1, so this is equal again, this is 2. Not orthonormal. In order to normalize it, the 1 minus 1, we can rewrite this one, 1 over square root of 1, 1. That's good. Now, it looks like with this formulation, what we can try is this equal to the identity matrix? So we can check this one. Most probably, this question mark, it is going to be confirmed, because let's think about this one, because well, you can check this one. You might observe that the A times A transpose is going to be equal to the identity matrix. Okay, so we can construct also other matrices that can serve as as transformation matrices, which can have this property where A inverse will be equal to A transpose, and the matrices, we can define the inverse of the matrix, because the inverse of the matrix multiplied by A itself, this is going to be the identity matrix. Important other elements, we can also record that the determinant of the inverse matrix, it is equal to 1 over the determinant of the matrix A. Okay, and but one thing that we can also see here is that these matrices, often the determinant is going to be 1 or minus 1, and this makes these also carry this wonderful. So actually, let's check the determinant here. This is the determinant of this matrix. This is 1 times minus 1. It's minus 1, minus 1, minus 2. Minus 2 times 1 over 2. So the determinant of this one, it looks like it's equal to minus 1. Okay? Because this is 1 over square root of 2, 1 over square root of 2. 1 over square root of 2 minus 1 over square root of 2. Determinant here is this plus 1 over square root of 2, 1 over square root of 2. Wait a second, no, it's not exactly this way. So we have a minus sign here. Then we have to take the negative sign here. So we know that the determinant is equal to minus 1. And these unitary matrices, they have a lot of several usages in different areas of numerical analysis. And probably, so these are some essential aspects which we start discussing chapter 6. Now, let's go over some of the slides, which, and wait a second. Okay, so these were some of the transformations. This is the discussion of how we calculate the Fourier transform, and all of the coefficients are shown in the and the first line. When you say the first line, is just this summation over n, where each element k, it's equal to a series of numbers, and overall we are going to get a matrix, which in this case is going to be 8 by 8, in case the data set has also 8 entries. Now, this is the coefficients of the discrete Fourier transform for 16 by 16, the matrix 16 by 16, which is necessary to transform a vector which is 16 values. Now, another thing we can add here is that for a long time, the functions, they were pre-written in a very easy form, in case the number of data sets is equal to 2 to the power n, because we have developed, or at least in the last century, one of the top 10 algorithms that was respected considerably. It was a fast Fourier transform, which enables a very small computational complexity, or very small computational time, when we calculate the Fourier transform of large data sets. Now, this is very important, considering that sometimes we may need to calculate the Fourier transform of a large volume of images, where the computational complexity it is much higher. And for a long time, we had people, whenever they are trying to calculate the Fourier transforms of data sets, they used to crop, or not crop. Crop is probably a good word for images. But they used to truncate their functions. So if they had 65 data points, they would throw out the last data point, have only 64, and take the Fourier transform of that one, because that was the best way that the fast Fourier transform could operate on. Here we are showing, let's say, if we have 16 data points, which is 2 to the power n, it can be represented that way. Here we are showing all the coefficients. And when we say the coefficients, we can write those in the matrix. Last week, if you remember, or in the previous session, we even wrote down how the fast Fourier transform coefficients can be written. And again, whenever we do all of these transformations, in principle, we are just going from one domain to another domain. And whenever we do these types of transformations, we have some specific resolution in one domain, and as a result, we're going to have also the reciprocal of this resolution in the other domain. Okay, so with reciprocal, we mean if we have some x resolution, which is some length scale in the real domain, in the other domain, we're going to have the inverse of this one. And also the unit of the resolution in the respective domains is going to be inverse of the other. So in principle, we are going to get that the area of these small elements that we see here, let me see if I can, no. I thought I could, no, apparently in this PowerPoint I cannot take notes. So in this në hapësirën fazore, quhet hapësira ku njëri bosht është boshti I vlerave reale dhe boshti tjetër është boshti I vlerave reciproke. Në rastin e transformimit Fourier, hapësira reciproke është një numër kompleks. Por ajo që kemi këtu ne, kemi që standard deviation in x multiplied by the standard deviation in the K space, this will always be equal to a constant. So here they are shown a couple of examples. Last time we also reported that as we are so in the time frequency plane, and this is time frequency, but this can also be represented as space frequency plane. With space, we mean the resolution in the real space, so we don't always have the Fourier transform of a function which is changing as a function of time. So we can have a pulse një sinjal EKG, të sinjalit që mund merret nga pacientët, mund marrim sinjalin e EKG-s, ai është funksioni i kohës, aty funksionin e mund t'i llogarisim Fourier transform, por njëkohësisht ne mund marrim nga një pacient, mund marrim dhe një imazh të enëve të gjakut për shembull, nëse për të analizuar nëse ka ndonjë shqetësim të enëve të gjakut, edhe aty do kemi nevojë për të marrë transformimin Fourier, pra mund të shkojmë në domen tjetër. Por një gjë që është kritike është që nëse ne kemi një rezolucion caktuar në imazhin që kemi në dorë, rezolucioni në domenin e ri do të jetë inversi i kësaj. Atëherë le të vazhdojmë, këtu kemi discrete cosine transform. Discrete cosine transform, kjo është një lloj transformimi i cili është ndryshe nga Fourier transform, pasi ka diçka, ka një frequency resolution që është 2 herë më e lartë se transformimi Fourier. Pra discrete, kjo është DFT. Sorry, this is discrete Fourier. This is also discrete Fourier. Sorry about this. For a moment, I was talking about discrete cosine transform. So this is, let me see for a moment. This is 1, 1, 1. So based on the discrete DFT, the numbers or the numerical values that we get in the first row and in the first column, these are all equal to 1. Oh, wait, here we have them. So if they're all going to be equal to 1. We're talking about the transformation matrix. And one thing which is common for all of these transformations is that all of these, they are normalized by dividing them by 1 over the square root of 8, or 1 over the square root of n, which in this case, n is equal to 8, so that's why we get that specific value. So this is going to be the DFT, the discrete Fourier transform. This is a discrete Hartley transform, so there is a different transformation. This is again a discrete Hartley transform, and here we see that the first line, it is a constant value, so it is independent of the data point. The second line, it is symmetric with respect to the center. So this is what we observe, but it is an odd function. It is not an even function. So we are saying that it is, my previous statement, it was partially wrong. So it is symmetric. Actually, it is anti-symmetric, the second row. Because odd function, they are anti-symmetric. The even function, they are symmetric. Even function is the function of y equal to x squared. So we know how this parabola looks like. So if we fold the xy plane with respect to the x-axis, we get that's a symmetric function. Again, if we see then in the lower sections of the, or in the 8th row, what we observe, we see that these functions are going to have a higher frequency. This is discrete Hartley transform. Here we get the discrete cosine transform, and in the discrete cosine transform, the frequency resolution is twice is higher than the fast Fourier transform or the Hartley transform. But we have to pay a price for this one, and the price we have to pay when we do the discrete cosine transform is that the number of data points that we have to consider, it has to be twice of the data points we calculate in the Fourier transform. So we get a higher resolution at the cost of having more data points in the real domain. So once we do this transformation, wait a second, so this is 8 by 8, okay, that's good. And yeah, this is 1 over the square root of 2. Let's see for a moment. where this is the transformation for the discrete sine transform. So, for example, uh, so if you think for a moment that we have one vector which is equal to the points 0, 1, 4, 9. So this is a function y is equal to x squared when x is equal to 0, 1, 2, 3. So here we have one data point here, one data point here, 1, 1. Then here this is 2, this is 3. 2 will be 1, 2, 3, 4. And then here we're going to get another point which is going to increase like this. Now, if we want to calculate the discrete cosine transform of this function, well, it is discrete because we just have these 4 points which are shown here in the figure. And immediately we said that we can have twice the frequency resolution of the fast Fourier transform, but in here we extend, how do you spell this one? This is extension, extend f, and we extend this f by doing 0, 1, 4, 9, and this is, we take the symmetric 4, 9, 4, 1, 0, and this is the, let's say, the new data set. And if you remember, let me see. So, and what we can do to this, vector, we can simply multiply by this matrix. So this is the transformation matrix of the discrete cosine transform. We simply multiply this 8 by 8 matrix with this vector, and once we do that, we are going to get. Now we can derive also the 8 by 8 matrix, but this might take some considerable time. And here we just need to determine what is the transformed data set by multiplying with this matrix. This is G, a vector, which is 8 by 1. This is 8 by 8, this matrix. And here we're going to get a series of number Pf. Now, if we calculate this, and in fact, this will also be equal to some function T1 and some function T2. And once we, when we calculate the discrete cosine transform of this vector, we are simply going to get the top part of the resulting vector. And again, what was this matrix A was? This was something like 0.35, 0.35. First row, it was all 0.35. We would multiply with 0.149, 0.149, and this is 0.149 again. And we can you can multiply this one also at home and see what the results are going to get. Okay. Wait a second. This is here, but we're going to see at least an implementation of the numbers when we discuss the hard transform. Hard transform is also a very interesting type of transformations. So this is wavelet transforms. Now, okay, so this is some interesting aspect. So here we see some type of modifications of images or two-dimensional signals, let's call it this way. And the image that we see at the very top, we see an original image which is 688 by 688. And in B, we see the discrete Fourier transform. And this is in B. And actually, this is something that we have, to some degree, mentioned before, that whenever we calculate the Fourier transform, often most of the information, it is right in the center. And in fact, when we say right in the center in the Fourier domain, it is going to be, it is symmetric with respect to the zero. So if we have an image which is xy, we're going to see the Fourier transform, which will be kx and ky, and right at the kx equal to 0 and ky equal to 0, there we'll have the lowest frequency, but also the highest intensity. Now, at the same time, we can also see that we have, for example, the bottom part. These are when you see the bottom part, the third line of these images, we are showing the Hartley transform, the cosine transform, and the sine transform. So it is interesting that the second image on the first line, second row, so if we give the interpretation using the matrix language, the first row, second column, we see in fact the summation of the cosine transform and the sine transform. Okay, so that's this is in principle the discrete Fourier transform, but things get a little more interesting when we're dealing with complex numbers, which happens when we have the DFT, because the Fourier transform, it can be the exponential function, or the kernel can be represented as cosine and sine using this operator, e to the power I theta. This is going to be cosine theta plus I sine theta. And in the kernel, e to the power I theta ikx dx, this one can also be decomposed as sine and cosine, and the integral is a linear function. So that means that these two integrals can be decomposed into two integrals. Now, again, here we have another type of functions, only that in this Walsh-Hadamard transform, we also observe that the type of transformations, it is more of a stepwise change of the wavelets, okay? So the sine and cosine, or at least the Fourier transform or the discrete cosine transform, the functions were changing a little more smoothly. So they were, to some degree, differentiable. But here we do observe a stepwise change of the functions. And let's see for a moment. This is some, I don't remember what type of transformation this was. This is figure 6 point. This is one-dimensional transform. ASI is used 6.35. Let's see, equation 6.35 and 6.36. Should I remember this one? But apparently this is the same as the Hadamard transform. Let me see, 0.35. This is slightly modified from that, 0.54. 6.28, 6.29. Okay, I should have 6.28, 29. This is let me think for a moment. This is images. Okay, so in fact, this type of transformation, it is the now I get it. So this transformation, this belongs to transforming just a vector from a vector to another vector. Okay, which means that since this one is 8 by 8, we can have a vector which is 8 by 1, right? We know how to do these. It's well, we've done this also before. When I say before, the simplest one, not to keep this one very questionable. So let's clear all for a moment. So we can represent a vector which is 0, 1, 4, 9. This is a vector which is 4 by 1. If we want to calculate the Fourier transform, this would be BB is equal to FFT of AA. Here we go, and we find a vector. So this is 4 by 1. We get another vector which is 4 by 1. That means that the transformation matrix, it is 4 by 4, okay? And what's interesting is that, let's do this one for a moment. BB divided by AA divided That's interesting. We can, by dividing BB and AA, but we got full of a lot of zeros. In fact, division by two vectors, this is something tricky, and it is not uniquely defined, so this might not be the best suggestion of how to calculate the transformation matrix. But in principle, let's call it CC is equal to an answer, and in this case, CC times AA. Okay, why didn't this work? Okay, this should not work because this should be multiplied with 8A transpose. Okay, so apparently, let's do this answer minus BB transpose. Okay, we didn't get them equal, and we did not expect, but because defining a matrix 4 by 4 using this operator here, this was not the smartest thing to do. Okay, you see this AA divided by BB. We can divide two vectors, but this is not going to be a 4 by 4 matrix. It will not be a unique result. The reason is that when we are trying to determine a matrix which is 4 by 4, we have 16 unknowns. Pra kemi të panjohura 16 vlera të ndryshme, por ne kemi vetëm 4 ekuacione. Pra kjo na bën të problematike. Por pse po bënim për shembull këtu, thjesht për kujtuar që ne mund të kemi një vektor që mund të jetë 4 me 1, siç është kjo këtu. Pastaj mund të bëjmë transformimin Fourier të kësaj, duke bërë FFT të AAs në rregull. Kthehemi te leksioni. Second, am I sharing the monitor? I think I am. Stop presenting. Okay, you are looking at the monitor. That's good. So let's come back to these slides. Now I also remembered what these were. So we said that we have this transformation, and now this was slightly different because this one is the transformation of a vector, and this one would be the transformation of an image. Okay, so if we want to calculate the transformation of an image, we're going to have slightly different values. So these equations, which is 635 and 636, they correspond to an image or to the rotation. Or let's think about like this. We can have a vector which is 8 by 1 and rotate it or change it by matrix 8 by 8. We can also have an image which is 8 by 8, and we want to calculate the transform of this one. That's why these two subsequent matrices, they are different. Now, for a moment, we just want to go over one interesting type of transformation, which is the Haar transform. Haar transform, you can have a look from the book on page. I want to find this one so you can follow me. Also, this is the frequency plane. This is images. Fourier related transforms. We just skip this one relatively fast and transform. So if you follow me from the textbook, we're talking about page 490. We have the Haar transform. Haar transform, it can be defined as shown here in this slide, where we have that the u, whenever u, it is defined as 2 to the power p plus q, where p, it is the highest order that that can approach to u, and q, it is the remainder. Actually, what we mean with this one is that if you insert text box. So let's say if u is equal to 7, then p it is equal to, so what is the closest value to approach to u? 2 to the power 2 is 4, 2 to the power 3 is 8. So we cannot put 2 to the power 3, but this should be 2. Then q, it is equal to 3. So this is one way how, and also u equal to 9. In this case, p should be equal to 3, because 2 to the power 3 is 8, and the remainder is equal to 1. Okay, so now we have this hard transform that can be defined as a function of u, where u, it is an integer value. Okay, so let's have a look here. And u can be, let me think for a moment, u can even be equal to 0. But when u is equal to 0, the hard transform, so u can be equal to 0, but then the function hu is a function of x. It's a constant value. This will simply be equal to 1. But then, if u is changing, then the value of these functions, so let's look, for example, here. This is when u is equal to 7. What is age 7? Let's see, age 7, sorry, age 7, I cannot write this one. Age 7, when x is equal to, let's say, 0.5. So based on this definition, on the second line here, let's see, this will be equal to, so x is going to be between q plus 0.5 divided by 2 to the power p. So in this case, this is approximately p is equal to 2. So this is going to be equal to 2, I believe. So this is equal to 2 based on the second line that we observe here. But we have also to check the value of x. It could be, yeah, I believe this is equal to 2. Similarly, what could be some other value here? U, it is really larger than 0. So it looks like if u is negative, then the function is going to be equal to 0. So it's a function defined only when u is larger than 0 with the respective other values. And by the way, actually, let's have a look at this one into more details. So what is q divided by 2 to the power p? Q divided by 2 to the power p. This is equal to what? Q is 3 divided by 2 to the power 2, 3 over 4. This is 0.75. Okay. This is 0.75. And x should be larger. Okay, that means that. Okay, wait a second. This is 0.75. This is the lower boundary for x. The upper boundary for x, apparently it's q plus 0.5 divided by 2 to the power p. So q plus 0.5, q is 3. So this is 3 plus 0.5. I want you to look at the second row in here. And let's look at the second row of this relationship here. Or probably we could also denote this one carefully using this line. Of course, let's try to mix. So looking at this equation, we see that when q is equal to 3, 3 plus 0.5 is 3.5 divided by 2 to the power 2, because 2 to the power p. So this is divided by 4, and this is equal to, what is 3.5 divided by 4? 3.5 divided by 4. 0.875. So apparently, the value of the function, it will be equal to 2 only for when x is larger than this and smaller than 0.85. Now, our x, if it is 0.5, apparently we will not consider this function, but we are going to consider this other function, minus 2. So this is going to be minus 2. Because in this case, preserving the same values, we can say that the Haar wavelet, when u is equal to 7, when x is equal to, let's say, 0.8, whenever this is 0.8, then this is going to be equal to 2. Why? Because these values, when x is equal to 0.8, that means that we have to consider this function because it is x is larger than 0.75 and smaller than 0.875. That's good. So this is one way how we can organize or at least write such a function. It is unique way of writing it, but they were developed actually some Haar wavelets. The wavelets in principle, they were developed starting from 1910, so around 110 years ago. And their usefulness, it was discovered around 40 years ago, or maybe 35 years ago. In multi-resolution analysis, the use of the wavelets, it was understood better. But this was just one of the examples. Now, okay, that's good. So now what is this H is going to produce? This H is going to help us construct the transformation matrix from one domain to another. Okay, so for example, the transformation matrix, this is the matrix A, which we wrote on the board, and we said that the transformation T is going to be equal to A times F. Now, this S of X, this is the inverse transformation kernel, which we wrote at the beginning of this session also. And actually, what we are going after is this. This is A. Now, in case the n is small, if in case n is equal to 2, we can actually, before we go this, let's have a look at, I thought, I thought we have solved this, sorry, this is 4 by 4. In fact, in this matrix, which is 4 by 4, this means that the n is equal to 4. So let's think for a moment. This insert text box. So when n is equal to 4, then we can say that u can be equal to 1, 2, and 3. Okay, so maybe let's do it like this. U is 2 and u is also 3. Now, when u is equal to 1, then based on the previous definition that we had, actually, what was the previous definition? Let's have a look here. It was 2 to the power p plus q. That's good. 2 to the power p, that means that p is equal to 0 and q is equal to 1. Okay. Then here, p, it will be equal to 1 and q is equal to 0. Why? So the q dyshi është barabartë në 2 në fuqit parë plus 0. And here, p is equal to 1 and q is equal to 1 also. So the 2 në fuqit parë del 2 plus 1 del 3. Okay. Then these are the values of u, p, and q, which we need those to define this h of u. Okay, and after we denote these, let's also notice that this matrix hn, this is defined for h0, h1, hn minus 1. So that means that once we set this u, which is 1, 2, 3, we need to determine h1, okay, sorry, h0. When u is 0, h1, h2, and h3. So this way we can construct 4 rows. The first row, this is going to calculate. Let me think for a moment. This is x. Yeah, this is x0 divided by n. I don't like this. Wait a second. I don't like this slide actually, because this doesn't look correct. When I say this slide, I don't like this one, because yes, and we should not like this one, because the second column, this should correspond, let me think for a moment, this should correspond for x equal to 1 to n. Okay. Yes. Këtu ka një gabim te kjo matrica në fakt e HN-ja. Dhe gabimi këtu është që text box. Let's do it like this. Here, x is equal to 0. This is x is equal to 1. This is x equal to 2. And this will be x equal to 3. Okay. Let's do it like this. At the same time, let's insert here. We say u is equal to what? U is equal to 0. This is u equal to 1, u equal to 2, and u equal to 3. So let's make this a little larger. So then, okay. So then, this value 1, this corresponds to a function h0, because u is 0, h0, 0, sepse 0 pisim për 4 bëjnë 0. Pastaj kemi h0, kjo do të jetë, kjo njishi këtu, kjo njishi I dytë këtu. Sorry. This one here, which we should make this one transparent, but not this much. So this one, corresponds in fact, this specific value that we just showed, this will be equal to h0 as a value when x is equal to 1 divided by 4. Okay, this is this one that we showed here. Then because this is x, right? X is 1. Then not this one, okay. Then no, sorry. This is something I need to, something interesting, which it's amazing. So I'd like to go to the recording of this class, to this moment, to this second, just to see how impressive this is. I wish we need to insert something else. Anyway, yeah, we need this. I was wrong. So that means that this other element here, which we can make this to some degree transparent, and we can fill it with some green color. So this one would be equal to h0 whenever x is equal to 2 divided by 4, okay? Because 2, it corresponds to this specific x here, which we can try to make it green, but these tricks are not the most expensive thing we can do today. Anyway, this is just how we try to read this matrix. And then once we do calculate all of these h functions for these specific values, so it looks like we are going to evaluate the first row, evaluated at 0, at 1 over 4, 2 over 4, and 3 over 4. Actually here you can see the trick. So the last column, it will correspond to whenever x is equal to 3. The second row, it will be, again, this will be evaluated at 0 divided by 4, 1 divided by 4, 2 divided by 4, 3 divided by 4. Only that the u, it will be kept 1. Then here we'll have the function h when u is equal to 2, evaluated again at 0, 1 over 4, 2 over 4, 3 over 4, and similarly. And then in order to substitute these values, we have to go back to this slide and calculate these values. If we do that, this is what we get for a matrix which is 4 by 4. Yeah. Now, so this was just one way how to be a little careful and deriving these specific expressions. Now I thought I had also here like an example of 8 by 8, but it looks like I have deleted it unintentionally, but mistakenly. Anyway, so yeah, so this was the example of a 4 by 4 matrix, which is shown in here. Now, similar to this, so this is just a little generalization of the information that we have obtained in the first slides of this chapter 6, and also in the first pages of chapter 6. Traditionally, we try to determine these transformation matrices A, okay? And this is how we do it. So we should just be careful, try to read directions and obtain these wonderful matrices. Here we have another type of transformation, which is simply a Haar scaling function. And Haar scaling function is just a function which is defined from 0 to 1. If this is defined from 0 to 1, we can also move the function. For example, if we do the phi from x minus 1, that means that the origin, it moves from 0 to 1. If we make this, we can also change the scaling. When we say we can change the scaling, we can also change the magnitude, as shown in the lower part. So we can change the position and the scaling. But now, as we're changing these, we should not forget that these are step functions which are going to multiply a data set. Okay, so it's like we have let's say it this way. So we have some data, some values in an array, and we are going to multiply with these kernels, and there will be an element-wise multiplication. When we say element-wise, so this Haar wavelet, it can have 3 to 4 different values. That means that we are going to encompass 4 subsequent values. Element-wise 1-to-1 multiplication will be conducted, and this element-wise multiplication and addition divided by some normalizing factor, it will be written down over one of the values. Then this kernel is going to shift 1 to the left or 1 bottom, and the same thing, it will be conducted again and again. Now, here, when we generate different functions, we can develop some scaling functions. Scaling functions, we can also see them here in this slide. So now, this slide here, this is a different Haar wavelet, which is similar to this definition. Here, the function, it was 0 and 1, and 1 was only between 0 and 1. Okay, so in the x-axis is between 0 and 1. This is how it is defined, because if you don't look at the image, it might look as if we're mixing the terminology. So let's move ahead. Here we have another function which is defined again between 0 and 1, but in the first half of the x-axis, it's 1. In the second half of the range where this function is defined, it's equal to -1, which in principle, this is how we can see it from here. We can again move the center or the reference point of the function, as it is seen in the second figure in the first row. And we can also change the scaling. And but when we change the scaling, we can also, we change in the same rate the width and the height. So if you notice carefully, the area of all of these positive value function, it will always be 1/2, okay? And this means that if we modify the amplitude by square root of 2, we can also change the width. So we can define it like this. So there is a, there is a width of the function and also the amplitude. So this, let's call it this way. Now, here we can see a series expansion of a function which is function y is equal to x squared. So the way to represent this one, it will be the following. You can assume that by adding up all the functions that we see here of the first order, second order, third order, fourth order. So adding up all of these oscillatory functions, they are not pure oscillatory functions for sure. We can get the function which is equal to x is equal to x squared. Again, let's see what this slide states. So now we can construct actually a filter bank. Now this terminology, some of you might come up along with this terminology, or at least with this aspect of filter bank, when you are implementing something. Often you're going to see this one, you can find some functions in the public domain, or you can find some functions which is written in any programming language. But what a filter bank does, it is a filter which has the same typology, but the parameters are going to change. A good example of this one can be a filter bank of Gabor functions or Gabor wavelets. For example, let's assume that you are trying to count circular shapes in an image. Okay, so there are several coins, and when you are trying to define these coins, you have to figure out, or you can apply a filter bank which will be kernels which can change where the radius can change. Okay, so you can scan the radius of these filters that can detect circular objects, changing the range from 1 to 25, let's say, and that is going to pick up a huge range or large range of the radii on the same image. So this would be a filter bank. The way to implement it, actually the mathematical aspect, this could be sometimes tricky, but sometimes implementing it could be relatively easier oftentimes. So here again, we have we have an implementation of Haar wavelet on a specific data set. So we have a function f of x, which is 1, 4, minus 3, 0. And the same way that we can calculate the what's the name? The Fourier transform, you can also calculate the Haar wavelet transform. The only thing that, not the only thing, but yeah, the only thing that you may need to figure out is that trying to identify how this, for example, help WHT Haar wavelet. No, apparently I did not find it right, so this is just one. Help for what? No. I was trying to, I don't remember, but there is actually, so if you search this one on the functions that are pre-written for MATLAB, you can easily determine that one. But let's go back. So this is just some numerical representation of how we can calculate the Haar wavelet transform using pen and paper. Okay, it's always good to do some calculations in this nature. For this one, actually, we also calculated the, what was this? The Haar wavelet for, no, what was it? Actually, this one that I tried to spend some time, it was this one, for example. So, and sometimes it is easier to generate the transformation matrix in matrix notation and then multiply this matrix with the values that may be given to us. So the same way that we spend a few minutes and we got this matrix 4x4, we can also, anyone can spend a few nice moments to determine the 4x4 transformation matrix, which does the Haar wavelet. But when we keep saying Haar wavelet, it could be, I believe this is, it would be this one, this type of Haar wavelet, and not this, because this is still Haar, but this is also Haar. And then let's move further. Now, okay, so all of these transformations that we have been discussing so far, they also do have their two-dimensional representation. Now, the two-dimensional representation, one way that we can represent this one in the simplest way is, let's say, so it is somehow trying to decompose an image into the low frequency terms and the high frequency terms. For example, here, this one, which is brighter, sorry, this is something like low frequency, and this is low high, and this is high low, and this is high high. Okay, so it is one type of decomposition which tries, and actually you do remember that when we found the matrix representation or the fast Fourier transform, that one, it is also didactic because it teaches us how we are implementing these transformation matrices, which in principle, they do have an equivalent of the frequency terms. So if you remember, the first row and the first column in the fast Fourier transform matrix representation, they were all ones. If they are all ones, those are DC factors. DC, it means that it's not AC. AC is just alternating feature something. DC is just a continuous value. It's a constant value. Let's call it constant value versus an oscillating pattern. Similarly, here, in this type of transformations, we can just interpret this one in the two-dimensional wavelet transform as low, 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 high, high, low, high, high. Now, here again, we see how how an image which is shown in this figure can be decomposed into different scaling orders, and we're going to see an example actually how we represent these. Now here we see some other type of functions, which and all of these functions, for example, they are Dalbechis functions, or we see this Cohen Dalbechis. So Dalbechis, it's a very nice mathematician. It's a lady, and she came up with these wonderful functions. Actually, personally, whenever I see this figure, yeah, this is Dalbechian family. I could not read this one, but Dalbechis function, this is how they look like. So it's like this function at the bottom, on the left side of the slide. These functions at the bottom, especially the second row and the third row. This is the family of Dalbechis. So whenever you see these, you can assume that we are not having a sinusoidal or cosine, a sine or cosine functions to pick up features, but we are having some functions which can have a higher resolution in time when compared to a resolution in frequency. Okay, so this is something that we can consider. And but again, this Dalbechis, all that remains for us to whenever we do the implementation, they are simply DWT. So actually, let me check this one. DWT, I forgot. So DWT, single level discrete 1D wavelet transform. So whatever remains for us to determine, actually, whatever we have to do when we implement these is just to figure out actually how we implement in a specific programming language. And just for a moment, but actually, yeah, the implementation is given right here. So if you have any question or if you want to do it, apparently we have an array of numbers. I was going to generate a few numbers, but let's do it like this. Let's paste this. No, let's say x is equal to 1 to 8. So we have 1, 2, 3, 4, 5, 1 to 8. And here we can calculate the discrete wavelet transform of this series. But this function, it has several features. So this dB1, this means Dalbechis of type 1. There's dB2, Dalbechis type 2, type 3, type 4. And finally, it looks like we get two series of coefficients which can be used to reproduce the same array of numbers. Okay, so here we found, let's say, what is called this wavelet. But let's see this one again. So this is a one-dimensional wavelet transform. Similarly, we could also calculate the two-dimensional wavelet transform. How would that be? Let's try to do, if we put just a 2 here, and okay, this is what we get. The two-dimensional, but we should not forget that this was a one-dimensional array. So that is the reason why one of the projections is equal to 0. Okay. Now, if we had a matrix which was XX equal to random number generators 8 by 8, is this size XX? Yeah, it is 8 by 8. That's good. So then this is XX. We can calculate the discrete wavelet transform two-dimensional of XX, and these will be the coefficients, and it looks like these coefficients which we calculate and which can be used to reformulate this matrix XX. Apparently, we have two matrices which are 4 by 4, and these are the coefficients. So now, what this is the way to implement it, and we have to also to see how. But what we are discussing here, we're discussing the theoretical aspect of these types of transformations. And as I said again, we can always derive the transformation matrices, which, as we said, they will be simply matrices which can be 8 by 8, 10 by 10, 11 by 11. But deriving them using a pen and paper, it is really time consuming. So if you choose, we can skip calculating these, as we did with a couple of examples previously. Now, okay. Now this is the keyword which you can pick up from this slide is that we can generate these filter banks, and these filter banks, they are somewhat smaller wavelets which are subfamilies of a larger wavelet. But let's move again. The filter bank spectrum splitting characteristics while having an analysis tree. Maybe we can go over these with an example. And here, for example, we have scanned fingerprint, which is the original image, and from this image we can obtain all the different levels of using the wavelet transformations. So this is the full wavelet packet decomposition, and apparently this is 8 by 8, I believe. So this is from a single image. One can obtain 63 different wavelet decomposition, which in principle, what they correspond to, we can imagine it in this way. So a function. So let's go back to the most fundamental aspect of Fourier transform. Fourier transform is really a very good trick to always go back there, explain something, and consider the other elements or the other transforms as being equivalent to that one. So any function, it can be described as a summary of oscillatory functions. Now these oscillatory functions, there will be a fundamental frequency, which is omega. So we have this omega, it can be 10 hertz. So we have an oscillatory function which has 10 hertz, plus another oscillatory function which is 20 hertz, plus another oscillatory function which is 30 hertz, another oscillatory function 40 hertz, 50, 60, 70, 80, and so on. So you can assume that you are producing functions which have higher and higher frequency. Now the same terminology can also be considered in the wavelet transforms. And what is interesting is that sometimes you can, one can decompose using the wavelet transforms. It can be Daubechi's. I'm using this because this is one that after Haar, actually there is Haar wavelet, there is Mexican head wavelet. This is something I never forget. There is also Daubechi's because it has found great use. It's very good to allocate edge information. And what can be done is that if someone is interested into preserving the edges of a specific image, for example, here in the fingerprint detection, it is essential for us to preserve edge information. So wherever there is a curvature of the shape changing element, probably some filters can do a better job. So if we have a huge data set, let's say we can have 1,000 students, and we have from these 1,000 students, we have also 5 different fingerprints. Okay, that makes a total of 5,000 images, right? 5,000 fingerprint images. And what can be done is that we can try now and to test a specific algorithm. What we try to do is that, let's say the first student is Angela, okay? And Angela has 5 fingerprints. What we can do is that we can match pairwise of these 5 fingerprints. And actually, it's just as an example. How many pairs can you construct from 5 different images? So Angela has given 5 times on 5 different days the same fingerprint, which actually you can use it also to turn on your cell phone or to turn on your laptop. So if you have 5 images, how many pairs you can construct? You get the combinations 5 by 2, which is equal to 5 factorial divided by 2 factorial divided by 5 minus 2 factorial. This will be equal to 4 times 5 divided by 2. So apparently this is equal to 10. So it looks like if we had 1,000 students, and so this is capital N, and we have also times 5 fingerprints, FP, per student, so this is N, this makes a total of 5,000 images. Now, one thing that you can calculate is that for a single student, we can have 10 pairs of 5 images. So this is the first image, second, third, fourth, fifth. So here we have 4 pairs, okay? Then here we have 3 more pairs. So if you add these, you should get 10. So if a single person has 10 similarities or 10, 10 pairs of which we can answer positively whether these belong to the same person. So let's ask this question. Are these from the same person? Are these fingerprints from the same person? This is the question. From the same person. Now, how many possible yeses can you produce from one person? We can produce 10 yeses because we have 10 pairs which should be the same, okay? So we get 10 pairs. But then, how many students do we have in total? Times 1,000. It looks 1,000 is 10 to the power 3, so this is going to be equal to 10 to the power 4. That's good. So now, we should get 10 to the power 4 yeses from the whole data set, okay? At the same time, we can also ask the following question. How many, so if we have 1,000 people, then the question is, how many no's can we get to this question? Are these fingerprints from the same person? How many no's can we get? This means that we have 999 people which are down here. So now we can calculate this at home. Okay, we can always deduce this. But overall, why did I keep this so long? Actually, for anyone who is working on biometrics, you have to have a very good understanding of this mathematical aspect of how you can compare the possible number of yeses and the possible number of no's, which would mean to get the possible numbers of true positives and false positive, true negatives and true false negatives, whatever one we forgot to say. We should get these numbers, but next to this nice, intuitive, wonderful mathematical aspect of how to calculate true positives and true negatives, we have also to have some information on the quality of the images of how we can improve these. So we can use biometrics measures of the same discussion we started talking right now. For example, we can try to determine to do all the possible matches between the images in one data set. And after all, we are going to get some curves that look like this. We are going to set some threshold, theta. If the similarity between two fingerprints is smaller than some threshold, we consider them to be the same person. This would be called true positive. That's good. And this would be true negative. And whenever we get these true positive, true negatives, this would be a score for us to get the accuracy. That's good. So now, we did one measurement, we got one accuracy for what? Let's say for raw images. We have fingerprint images which we have not modified at all. Then we can recalculate the same accuracy after we have implemented some wavelets. These wavelets, it could be Dalbatius wavelet, and then researchers have found out that working on fingerprints recognition, or probably iris recognition, or face recognition, they found out that the accuracy can be improved as a function of different wavelets transformations. Sorry, let me think this for a moment. I'm sharing the screen, but probably it's time to stop sharing the screen just for a few seconds. So what we are trying to represent here is that we were discussing the possible calculation of the accuracy based on image analysis, and we can get an accuracy from the raw images, not edited at all. And those, so the accuracy here is going to be from 100%. So this could be something like 80%, but then we can have fingerprint images using Dalbatius filters of type 1. Probably the accuracy is slightly higher. Then we can have Dalbatius filters BB type 2, or we can use another wavelet, which is higher wavelet, and probably the accuracy might change. So a good exercise would be the following. We can pick up the whole data set of fingerprints. We can find the wavelet decomposition. And some of these wavelet decomposition, it might not even mean much for the human perception, because the information that can be carried, it can be just the edge information, which somehow could be the fundamental features in determining whether it is person 1 or person 2. Okay, we don't know. Maybe the major features might be hidden in some, who knows, in some horizontal curvatures of how the fingerprints are changing along this axis. Maybe the change along the vertical axis of this fingerprint, it does not carry much information, but we have no idea to figure this out unless we filter our images with some wavelets which could be selective along the x-axis or selective along the y-axis, which the simplest way to think about this one would be trying to find the derivative along the x-axis and the derivative along the y-axis. Okay, so so again, whenever any one of you is working with images, the analysis or the work, it can become complete once the data set, the signal, it could be also a signal in one dimension, or images or videos, the accuracy or the efficiency of detecting an object, efficiency of segmenting an object can become better or higher once we have, or once we implement some wavelet transforms into our data sets. Okay, so I'm sure that some of you do have some projects which are on image analysis, and probably you can conduct your calculations using the raw images, and then afterwards you can redo everything once you have implemented the same algorithms, not on the raw images, but on the, let's say, on the wavelet decomposition of this specific data sets. Now, I have a couple of examples of how we implement these data sets on images, but probably just as examples or as implementation, I can share to you the codes on Google Classroom, and you can implement them on your own. For now, do you have any question for what we discussed so far?
No, Professor.
Okay. Thank you.